Let's cover one more exercise with the Fourier series. Now we have an op-amp with a set of resistors and one capacitor connected in this fashion. And our input is now a triangle wave with a period of 4 pi milliseconds, a volt peak to peak of 10 volts or an amplitude of 5, and the respective values for resistance and capacitance here. And our goal is to find the V0 of t, finding the first 4 non-zero terms of the Fourier series. Alright, we're going to apply these 5 steps in order. We'll start with step number 1, the Fourier series of the input in an alternative form. So alternative form is this one that has the amplitude and the phase. And let's use the tables and find the Fourier coefficients for our triangle wave. And if we do that, we find the following Fourier coefficients. Alright, we have an with a times a n pi square for n odd. We have an equal to 0 for n even, and bn is equal to 0. No DC component. Alright, let's write that down. The DC component is 0 volts. Our an is 8 times our amplitude, which is 5, just for n for when n is odd. Bn is 0. That means that my amplitude is equal to just the an, and my phase is going to be equal to minus the arctangent of bn over an. If bn is 0, that means that I get 0 degrees. We substitute those values on the alternative form and we get the following expression. Let's go over step number 2, analyze the circuit in DC. So we're trying to find V0, this first V0 over here in yellow. My Vs of t in DC is 0 volts, we just saw on the previous step. And in our case here, our capacitor is going to be an open circuit. So if you don't know if it's an open circuit, remember and recall that the current flowing through the capacitor is C times dVc dt, or the derivative of the voltage across the capacitor. The DC means that everything is steady or quiet, so the derivatives are 0. So that means that I have no current flowing through the capacitor. So if I have no current flowing through the capacitor, I know that the voltage at the positive terminal is going to be the same as the voltage at the negative terminal, and this is because we have our op-amp in an amplifier configuration. And 0 volts over here, that means that my V0 is going to be 0 volts. I have no current flowing through this branch over here. Alright, so we plug that value over here and we go over step number 3, which is analyzing our circuit in AC. So now we want to apply those Laplace techniques into our circuit. Okay, so I substitute my input by the respective Laplace, output by the respective Laplace, the current, and I put the respective impedances. So my ZC is going to be equal 1 over SC. C is 0.1 micro, and the ZRs become 20K and 200K. Alright, from here I'm going to write what I know about this op-amp in amplifier configuration. I know the current flowing inside of the terminals is equal to 0. I'm going to write also a current here called I2, and I can apply KCL at this node. I also know that the voltage at the positive and negative terminal is equal to 0 volts. So if I apply KCL at that node, the current entering is equal to the current leaving, so IS is equal to 0 plus I2S. And then if I apply Ohm's law on each one of these components, IS is going to be this potential minus 0 divided by the respective impedance, and it's equal to 0 plus this voltage 0 minus V0 over ZR2. Alright, so I substitute the impedances by the respective values, and now if we massage this equation, if we reduce to the same denominator over here, this value here goes up, and then we multiply by 200K and we get the following expression. So now we are at this point that we can substitute S by j omega n. Remember that there are a set of conditions that need to be true in order to apply this substitution. Outside of the scope for this video, I'll address these on another video. For now, let's just assume that we can do that. So let's find that omega, that frequency, and we know the period 4 pi milliseconds. We find the frequency, and then we know that omega is equal to 2 pi f. So we get 500 radians per second. Alright, cool. So we have that, and now we're in good shape to substitute S by j omega n. So I plug the omega into there, and then multiply by the respective values, and we get this equation over here. Now we substitute our input by the respective polar form of our Fourier series. So we found this on step number 1. So I substitute by the respective amplitude and phase. The phase is 0, that's why it doesn't show up here. And now that I have here, I can multiply this part with this complex number over here, and I get this part. And from here, all I need to do now is to find the respective. I'm going to put this in polar form because I have a division. It will make my life easier when I do the division of complex numbers. So the polar form of this number is the amplitude and an angle of -90 because of the minus j. And then on the bottom, just apply the respective amplitude and arctangent. Alright, so we have that division. So all I need to do is this one divided by that, and this angle minus that angle. That gives you the amplitude and the respective phase. We're done with step number 3. Now on step number 4, we're going to find the Fourier series terms. Alright, and remember that we're trying to focus only on when n is odd. And we want to find the first 4 non-zero terms. So that means that I will get n equal to 1, n equal to 3, n equal to 5, and n equal to 7. I write that all down. And last step, step number 5, we're going to plot that information and see what we get and validate our answers. So let's see that on Desmos. We got the following information. I'm extracting this from Desmos, and I'm plotting here one of the graphs here in blue with the 4 non-zero terms, and then with 500 terms. So notice that with the 500 it approximates better to your final answer. Let's use now Falstad and simulate the circuit and see if we get this answer. And here we got exactly the same answer with an input with a triangle wave with an average value of 0, and I also get an average value of 0 on my output, and I get exactly the same answer that I plot with Desmos. That means that you are on the right direction.